Hello, welcome back to Engineers Escape. My name's Jake, and today we're going to be looking at basic electricity. Alright, so basic electricity. What is electricity? Electricity is a form of energy resulting from the existence of charged particles, such as electrons or protons, either statically as an accumulation of charge or dynamically as a current. So let's talk about what that really means. So electricity, you see it has the first several letters of the word electron. So you can kind of think of it as the energy from electrons. Statically means that there's no movement. In other words, that would be static electricity. That won't be the main focus. Typically when you think of electricity, you think of it being dynamic. And dynamically means with movement. In other words, it'll be electric current. And that's going to be our focus. So, one more time, electricity is essentially energy from electrons, and you usually think of it in the form of an electric current or moving electricity. So where do we find electricity? We find electricity all over the place, but just as for some examples, it's used in your car, in your cell phone, in light bulbs, your TV, and your washer and dryer. So how does electricity work, and why does it work? Well, we're going to be talking about some electrical fundamentals, and there's three basic parameters that you're going to want to understand. And a parameter is just a thing or a quantity to measure. You can think of it like using a measuring tape to measure meters. You see the word parameter actually has the word meter within it. So again, it's just a quantity or something to measure. The three basic parameters are voltage, current, and resistance. And we'll talk about each of those. Voltage. So voltage is a potential difference or a difference in potential. And the word potential just means the possibility of doing work. You can measure the voltage across the terminals of a battery using a voltmeter, and voltage is also known as an electromotive force, and that shows the ability to do work by forcing the electrons to move. The unit of measure for voltage is the volt, or just a capital V for shorthand, and the symbol for voltage is a capital V, or some people use a capital E. I prefer the capital V. The next thing is current, and current is the flow of electrons. So when a battery is connected to a light bulb, current will flow out of one terminal of the battery through the light bulb and back into the other battery terminal. And the unit of measure for current is the ampere. Most people just call it amps, or you can see it written down in shorthand as a capital A. The symbol for current is a capital I. The last one we're going to talk about is resistance. Resistance is the opposition to current flow. Materials can be considered conductors, semiconductors, or insulators. Conductors have many free electrons and allow current to flow easily. On the other hand, insulators have few free electrons and make it very difficult for current to flow. Good insulators practically do not allow any current to flow. And for an example, conductors, usually you think of metals, such as copper, is typically used, and insulators like plastics or rubbers, just to give you a couple examples. And you'll notice that a lot of wires will have some sort of plastic or rubber insulation around the outside of them, and that's for safety, so that if you would go to touch it, you wouldn't get shocked in most cases. The unit of measure for resistance is the ohm, or omega. Yeah, so that upside down horseshoe looking thing, that's just the Greek letter omega. You can think of it just like any other letter in the alphabet. I don't know why they chose to use the Greek letter. But once again, that would just be read if you see that symbol as ohms. and the symbol for resistance is a capital R. I prepared a couple analogies for you to help you understand electricity better. The first analogy or comparison is water flowing in a pipe. So if you imagine there's a water pipe and there's water flowing through it, you can think of the voltage as the water pressure or the pounds per square inch that's actually in the pipe. So if you had a pressure gauge on it, you might see 75 psi or 100 psi, and that would be related to electricity as kind of the voltage. You can think of the current as the flow of the water going through the pipe, maybe in gallons per minute. So if you've got a lot of current, you might have maybe 5 gallons per minute of water is the comparison, but if you didn't have as much current, you would have maybe 2 or 3 gallons per minute flowing through the pipe. And you can think of resistance as the size restriction of the pipe's inside diameter. In other words, the less wide the pipe, the harder it is for the water to flow through it. So if you have a big pipe, say 2 inches wide, that's going to be less resistance. But if you had a small pipe, maybe half an inch diameter, it's going to be harder for the water to flow through that. In other words, it'd have more resistance. Just wanted to draw these out for you here so you can get a better visual. So for analogy number 1, we have our pipe. And we're just kind of looking at a small section of it. So there's still more pipe on each end. And imagine this is filled with water. That's kind of what these squigglies are. So if you came up here and you had a pressure gauge coming off the top of here, and the pressure read, I don't know, 100 psi, or maybe it was 75 psi. You can consider that as similar to your voltage, with the higher the pressure being a higher voltage. Now, for our current, you would think of that as the actual water flowing through the pipe, essentially how fast it's flowing through there. So you might think of that in gallons per minute. So if it's not flowing very fast, maybe it's 3 gallons per minute. But if it is flowing quite quickly, you might think maybe 5 gallons per minute. And that's similar to electric current, or capital I. Now, if you looked at this pipe here, the end of it, took a cross-sectional area, you would see something like this. And this would be the diameter across. Maybe the diameter is 2 inches, or maybe the diameter is smaller for a different pipe, maybe 1 inch. So essentially, the smaller the pipe is, the harder it is for the water to flow through. And essentially, the smallness of the pipe you would consider kind of similar to our resistance, or capital R. So if you have a big pipe, it's going to be easier for water to flow, but if you have a small pipe, it's going to be more difficult for the water to flow through it. The second analogy you can think of is marbles rolling on a wooden track. So you have several marbles lined up and they're on a wooden rail or a wooden track. You can think of the voltage as being similar to the mass of the marbles. In other words, if you had small marbles that don't weigh very much, the voltage would be low. And if you had large marbles, you could think of that kind of as the additional mass being kind of as a higher voltage. The current is similar to the speed. You might think of that in meters per second of the marbles rolling along the track. So a low current, they would be rolling slowly, maybe 1 meter per second along the track. But if you had a high current, it'd be maybe 5 meters per second. So they'd be rolling really fast along this track. And resistance is similar to the bumpiness or the roughness of the wooden track. In other words, if you have a track that is really bumpy and rough, it's going to be harder for you to roll those marbles down the track, and that would be kind of considered a higher resistance. But if you had a track that's very smooth, the marbles are going to flow pretty freely, and that would be related to a lower resistance. Analogy number 2. So say we have a bunch of marbles. And they are sitting on a wooden track. Rather, they're rolling on a wooden track. And once again, don't think of it just as a few of them like I have drawn here. Just think of it as it continues from both sides. Okay? So if you looked at one of the marbles, and if you had a smaller versus a bigger marble, the small one might have a mass maybe of 50 grams, but the larger one might have a mass of 100 grams. If there were different marbles on the track and they were all bigger, you would kind of consider that to be similar to your voltage, or capital V. Now, similarly to the water, if these are rolling here along the track at different speeds, so maybe the speed was, I don't know, 5 meters per second, or maybe it's 10 meters per second. So if they're rolling kind of slowly along this track here, maybe that's 5 meters per second, but if they're rolling really fast, maybe that's 10 meters per second. And that's similar to your electric current, or capital I. And the last thing I'm going to talk about is if you were to look at this track here, maybe it's pretty smooth, or maybe the track is kind of bumpy. So essentially the roughness of the track is kind of how resistive it is. It'll make it harder for the marbles to roll. You have a really bumpy, rough track as opposed to having a smooth track. So the roughness of the track is similar to our electrical resistance. So some uses of electricity, electrical energy can be converted into other forms of energy and vice versa. And that's why it's so useful to us. You can use electricity and convert it into heat, for example in a toaster or a stove heating element, or an electrical heater that you plug into your wall. It can be converted into light, such as in light bulbs in homes, in headlights of cars, or in traffic signals. It can be converted into magnetic energy for use in electromagnets and transformers. And it can be converted into movement, or in other words, mechanical energy, like in electric motors that turn fans, electric mixers, like your egg beater in your kitchen, or in drone propellers. Okay, I hope you enjoyed that video on basic electricity, and if you have any questions at all, just be sure to leave a comment below and I'll get back to you. Thanks for watching.